Hello, my name is Charith DeSilva, and I'll be talking about my research this summer, investigating the capability of machine-learned interatomic potentials for materials research. So in computational material science, there's a variety of techniques you can use to simulate materials, two of them being classical interatomic potentials and density functional theory. So with classical interatomic potentials, these are mathematical expressions that can be used to calculate the potential energy of a material system. So using these classical interatomic potentials, these are very fast. However, they're not very accurate and only work for very specific material systems, depending on the potential. On the other hand, we have density functional theory, or DFT, which is a quantum mechanical modeling approach, which is very accurate but takes a lot of computational resources. So there's always this trade-off in computational material science that you're trying to balance. So one way of balancing this is by using machine-learned interatomic potentials, or MLIPs. So machine-learned interatomic potentials are an interatomic potential that is created through a machine learning model, which is trained on a large data set of DFT materials data. So with these MLIPs, they're a lot more accurate than classical interatomic potentials, and they are a lot faster computationally than using density functional theory. So in my project, I'll be looking at one machine-learned interatomic potential in particular, Maze MP0. So this is a foundational machine-learned interatomic potential, meaning that it's designed for use in pretty much any material system right out of the box. And it has shown good results in predicting the properties and dynamics of a variety of materials and molecules. So the two systems we'll be looking at are liquid metal catalysts for water splitting. So we'll be modeling dynamic interfaces using molecular dynamics, and the vacancy formation energy in high entropy nitrides, so calculating defect properties of various multi-component materials. So far in the summer, what we have done is quite a bit of validation on Maze MP0 with our reference DFT forces. So on the left here, we have a parity plot of Maze MP0 forces on our liquid metal systems compared to reference DFT data. And we can see here that the Maze MP0 machine learned interatomic potential has pretty good results compared with DFT. And then on the top right, what we have also done is use some very simple molecular dynamics, and we're able to simulate water dissociation with Maze MP0 in our liquid metal system and show that it is possible with this machine learned interatomic potential. We've also calculated the vacancy formation energy of a variety of sites in our high entropy nitrides and done a parity plot of Maze MP0 and DFT vacancy formation energies. And we've also found a pretty good correlation between Maze MP0 and DFT in our high entropy nitrides. So this is a good start. And for the next 4 weeks or so of my internship, what we'll be doing is more advanced molecular dynamics calculations to fully understand our liquid metal systems and trying to improve the Maze MP0 model by fine-tuning it with already existing DFT data that we have here at Sandia. Thank you for your time, and I'm happy to take any questions.